And we're back. Oh, what a day it is. Oh, goodness. The technical issue that I was facing was actually multifold. I'll run through my list of issues in a moment. But as a first and foremost, good morning. Welcome to Snowpocalypse. And please leave me a comment in the chat. That'd be fantastic. And I could see everyone's wonderful 7:30, 3 or 4 inches of snow comments. I don't know. I don't even know what I'm saying anymore. It's it's been it's been interesting. I knew that there was going to be a snowstorm, and originally the message came out and it was just for students, and the teachers are like, well, what about us, and then they're like, oh yeah, by the way, teachers, you're going to be teaching still. And I'm like, from home. I'm like, okay. Oh, and the school's open till 8 p.m. Mind you, they gave us this message at 7:30, but they're like, oh, the school's open till 8 p.m. if you want to come in and get your stuff. I brought home some of my stuff. I did not bring home all of my stuff. I had written out, prepared notes, for the lack of a better term, for you guys, which I'm still going to do something today. Oh, you better believe I'm going to do something. But I had prepared notes at home, and they're sitting on my desk. I'm like, why didn't I bring them home? Makes me sad. I'm a little teary-eyed. But the other technical issue that I was having was that my kids have made it a habit to wake up in the middle of the night and climb into bed in mom and dad's room, and I was out and about doing my stuff, but I'm like, I got a live stream, and it's like 7:10, and they're still all sleeping in bed, and I'm like, ugh. But my kids get to experience a snow day. I don't know what kind of snow day traditions you have at home with your family, but my wife has made it a pretty consistent tradition. Pretty consistent, pretty much since the first year we were married. But she's made a pretty consistent tradition that whenever there is a snow day, or a big snow day like today, she always makes pancakes and homemade syrup. Always. Every time. So, I don't know what you guys do. That's what I do. Or that's what we do here, or whatever. Anyway. But yeah. I'm stalling to kind of give people an opportunity to get in, because it says I only got 16 viewers right now, but we'll see what happens. Here's the rundown of today. My hope and goal is not to keep you the entire time. It's a snow day, but at the same time, they want us to, teach synchronous instruction, so to speak. So, I'm sticking with the general plan that I have, that I've outlined from, my lesson planning, but it'll be somewhat amended. First, there was an AP planning meeting yesterday, amongst all the AP teachers, the AP coordinator, the curriculum supervisor, the principal, and we were discussing how we would like to handle the AP test. As I mentioned to you last week, the College Board is offering 3 session windows that are like 2 weeks each. And I thought that, I don't know what I thought exactly. I thought that students would get to choose, or we would all do the same thing, or I don't even know what's going on. But apparently what they want to do is they want the teachers to make the decision that is best for the students. And one of the things that we discussed was the benefit of actually taking an in-person test. And even if they do a digital test, they still may have people come in to do the digital test. Right now, it's still kind of all up in the air, because apparently, this is the first time all the AP teachers got together, and everybody has a different opinion. But for the most part, a lot of people are either leaning towards the first session or the second session, for the rationale of, let's, do the first session, knock that whole thing out, have the best chance, have it all be fresh in our minds, not get burnt out. Some people are saying the second session because we'll have a couple extra weeks to study and to review information. I am going to, at some point before the end of this week, send out kind of a survey question to you guys to kind of get your opinion as to what you would prefer. This would not be your official choice, but what you would prefer in terms of testing, whether it be, I'll give you the dates for the windows of testing, the type of testing, in-person paper, in-person computer, or whatever else they're offering. Because again, College Board, I don't really think knows what they're doing, but yeah, I'm going to be sending you out a survey, so don't worry about that. Second, I'm going to, where is it? I'm just double checking right here. There we go. I have not made the video yet for page 465. I ran out of time yesterday. I don't know if I'll have time to do it today because I teach multiple classes and I have snow responsibilities to get to. But I still am planning on making that video for you guys to go over those particular questions, especially for any future test that we may have. But I would like to assign you a quizzes minor. And this is what I'm going to be doing. I'm going to be assigning you a quizzes minor before the end of today. I will make it multiple chances at taking it. I believe I'm going to give you 2 chances at taking it. And that'll be posted sometime before the end of today. When it will be due, I'm pretty confident that I'm going to have it due before Monday morning's class, I should say. So you should have the weekend to get it done. So, So, number 1, little late, technical issues. Number 2, AP planning meeting. I'm going to send out a survey to you guys. Number 3, I'm going to be assigning you a quizzes minor on the chapter that we just did, sampling distributions. That will be due before Monday morning. And yeah, here we are. It's such a weird day. Again, I don't have any of my stuff, so a lot of this stuff is just kind of being, well, the stuff that I'm going to be showing you in a moment is going to be kind of brought up on the fly. So here we go. If you do not already have them out, I'm going to need those notebooks out and open. I can hear the cheers. I may be, I may live in Manahawkin, but I can hear the cheers resonating throughout all of Barnegat. Yes, Mr. Markey, it's time for stat. Yes. Okay. Don't act like you love it. Or don't know it. That's wrong. I don't even know. I haven't even had my coffee this morning, to tell you the truth. Okay. Can I change this brightness? My word. Can I change that? No, I don't like that. No, that's terrible. That's a little bit better. Okay, whoa. Yeah, it's really bright. Whatever. Okay, let's see if I can't fix this on the fly. Today is the 11th. Yeah, that's really bright. How do I fix that? Goodness. Nope, that's reversing it. That's that. Let me try one thing. Let me try one thing here. Try to fix this thing up here. It's a little better. Yeah, that's a lot better. Yeah, that's a ton better. I'm going to go with that. Excellent. Okay. Good. And of course, if you have any questions along the way, I have the chat right here, right in front of me. I can see all of your wonderful, statements. So, anyway, here we go. This is going to be an intro to confidence intervals. Now, confidence intervals is the other side of the coin compared to sampling distributions. And let me give you kind of this bullet by bullet point statement. In sampling distributions, given a population mean slash standard deviation, which I talked about that last time. Of course, the population mean could be a categorical data with a proportion, or it could be quantitative data with an actual numerical mean. The standard deviation, if it were categorical data, proportions would be the square root of PQ over N. If it were quantitative data, you would have the population standard deviation, sigma, and you would have to divide it by the square root of N. In sampling distributions, given a population mean and standard deviation, we found the chance or probability of seeing, I don't even know how to exactly word this to make it grammatically correct, but of seeing such sample statistics. That makes kind of sense. I mean, I'll explain it in better detail, but basically, okay, hey, we got this sample statistic. What are the chances that we would see these sample statistics given that this is the population mean and this is the population standard deviation? Oh, well, here are the chances of that happening. Running through all of the assumptions and conditions that we would normally have to go through. And then we would see the chance of that happening. And if the chance of such an event happening, seeing those sample statistics, if it were less than 5%, then certain things could be called into question. But if the probability of such a thing happening were greater than 5%, then we'd be like, well, no, that can happen. That can happen. Fun fact about 5%. 5% is the typical gold standard threshold in statistics. It can be changed. I mean, you could make your standard of threshold 1% or 10%. You could make your standard of accepting such data as stronger or weaker depending on where you move that threshold. But 5% is the typical threshold. And the question is, well, like, how in the world did statisticians decide that 5% was the threshold? And I kid you not, it was literally a guy who said, 1 in 20. He was just literally like, 1 in 20. 1 in 20 sounds good. 1 in 20. Okay. 1 in 20 is 5%. It almost feels like it's being made up as it goes along. It's like, it looks straight enough. It looks nearly normal. Close enough. My goodness. You ever hear the phrase, close enough only counts in, horse grenades? You ever hear that phrase? It's an interesting phrase. It's a dangerous, disgusting sport, horse grenades. You're going to be wondering whether or not it's a horse being thrown as a grenade or if it's a horse filled with grenades, but that's besides the point. Back to this. That's sampling distributions. Confidence intervals. In confidence intervals, given the sample statistic, we are, we are able to construct an interval that, and I'm going to underline this word, hopefully captures the true mean. In confidence intervals, you are not given the population mean. When I say true, I'm going to put underneath population. There we go. In confidence intervals, given the sample statistic, we are able to construct an interval that, and again I emphasize the word hopefully, captures the true mean. Believe it or not, something like confidence intervals is used all the stinking time. Again, it's the other side of the coin of sampling distributions. In sampling distributions, you have the population mean and standard deviation, and now you're looking to find the chance of seeing such sample statistics. But in confidence intervals, you don't have the population mean and standard deviation. You have the sample statistic, and you're constructing an interval that hopefully captures the true proportion, or true mean, or whatever it is. It ends up being, depending on the type of data that you have, of course. It's very strange. And that may seem like, what do you mean hopefully captures the true mean? This happens all the time. If you've ever seen a poll, you know, they do polls all the time in regards to politics and elections and things of that nature, but if you've ever seen a poll, for example, Mr. Markey's running for governor of New Jersey. Clearly, I am the superior choice. But since Mr. Markey is running for governor of New Jersey, they wanted to get, okay, well, if it was Mr. Markey versus this other candidate, who would everyone vote for? So they go out and they conduct a sample and they gather the results of said poll and they say, well, Mr. Markey got 51%. So Mr. Markey's winning 51% to, 49%, let's just say, 51-49. But as with any poll, they typically also include a margin of error. Now, believe it or not, that margin of error is exactly what we're talking about in regards to confidence intervals. You see, because we don't know the true proportion of people in New Jersey that would vote for Mr. Markey for governor. We don't know the true proportion. The only way that we would find the true proportion is if we sampled every single person in the state of New Jersey, which clearly is not feasible. So we have to take a small sample. Well, how big of a sample? We'll talk about that. We will talk about that. But how big of a sample? We'll see. And then with that sample, well, I got 51%. But there's a margin of error of 3%. Now, if that margin of error is 3%, that means plus or minus 3%. If 51% would vote for Mr. Markey, that interval goes from 48% up to 54%. Now, what that interval is attempting to do is hopefully capture the true proportion of people in New Jersey who would vote for Mr. Markey for mayor. I'm sorry. That's an old comedy sketch idea that I had. I'll tell you super quick. My friends and I, when we were in high school, we did not have a garage band. We had a comedy sketch team, and we wrote comedy sketches, and we performed live sketch comedy. And one of the ideas that my writing partner and I came up with was Markey for mayor, in which I would invest. It would be like this multi-staged video series of my journey attempting to run for mayor of Barnegat. And ultimately, it would culminate in me finding out that, and this is true, Barnegat doesn't elect their mayor. Barnegat elects a town council, and then they select the mayor from amongst that town council. So, Mr. Markey, you had a comedy sketch team in high school? Are you surprised? You shouldn't be. Anyway. Oh, back to this. Okay. So, I'm going to deal with confidence intervals of proportions today. I'm just going to stick mainly with that for the time being. Confidence intervals of proportions, since that's the most common way that we can go about doing something like this. Because, again, people go out and they don't know the true proportion of people's opinion on a certain topic, but they go out and they collect a sample, and they're able to report on the news that, oh, so-and-so has a lead in the election. Well, how are they able to report that? How confident are they? Well, we're going to get into those details. So, given a sample proportion, p hat, because p hat is the sample proportion, and a sample size, n, the following interval can be constructed. That interval is p hat plus or minus z star, which I'm going to discuss what z star is in a moment, times this wonderful little thing, which again, I'll explain what that is in a moment. Now, first of all, the interval is centered around p hat. P hat is in the middle, and then you add and subtract the same number to create the interval. And again, that interval is hoping to capture the true proportion, because we don't know what the true population proportion is, which would be indicated by p. Notice I put SE. That is not a typo. We don't know the standard deviation. The standard deviation would be the square root of PQ over N. But we do not have P or Q. We don't have that. We are hoping to capture that, but we don't have it. We might never know what it is. And since we don't have it, we cannot construct the standard deviation of the sample. Typically, I would put SD of p hat or sigma of p hat or something like that. Can't do it because I don't have it. The standard error is what they call it. Standard error. And the way that it is constructed is like this. Now, last class, I made a huge deal about the mistake that I made that I corrected in our notes. If you did not see that correction, you need to go back to Tuesday's lesson at the beginning so that you can see that correction. The standard deviation of the sample is the square root of p cubed over n using the population parameters. But since we don't have it, the standard error would be the square root of p hat q hat over n, just for the sake of argument. The z star represents the confidence of the interval to an extent. It represents a critical value. The critical value on a normal curve. Or, you know what? I'm going to change one little tiny thing. The critical values. But there's only one z-star. I know there's only one z-star. But I want to be very clear about critical values. How we calculate that, I will show you in a moment. How confident do we want to be? Clearly, we would love to be 100% confident. You can't. You can never be 100% confident. Sorry. Sucks to be you. Typically, when you put out a poll in regards to like elections or opinion polls or whatever, again, I say gold standard, but the gold standard is to be 95% confident. That is the quote-unquote gold standard. We hope to be 95% confident that we have captured the true proportion. If I say that I am 95% confident, then that actually determines what the Z star is. And I'm going to show you how to calculate that in a moment. I could be 90% confident. I could be 99% confident. You will never be 100% confident. You can't be. It mathematically cannot happen for a confidence interval. Okay. So let's see what happens with a basic example. Somebody goes out into the state of New Jersey. It goes out into the state of New Jersey, and they sample 1,000 people. Let's just say there's a sample size of 1,000 people, and this is quote Markey for governor. This is Markey for governor. And they find within the sample that 51% of people said that they would vote for me. Cool. That's all the information that we have at this exact moment. So, I would like to construct, and I'm going to get into the more details of, Z-stars in a little bit, but I want to construct and interpret a 95% confidence interval. Again, the goal and the hope is that we capture the true proportion. Will we capture the true proportion? Maybe. Maybe not. But we can be a certain level confident, which I'm going to get into those interpretive facts in a little bit. So, we would do something like this. First, let's talk about the 95%. I would like you to draw this. There we go. This is your typical normal curve. And I would like to attempt to capture the middle 95%. Now, I don't have the calculator that I have at school on my computer, but I do have this TI 84 Plus, which makes me feel powerful, I guess, so to speak. I don't care. Here's what we're going to do. We're going to go inverse norm. And I would like you to do the same thing. I hit second vars. You can go to inverse norm, which is option 3 right there. Now, on my calculator, it does not have the same interface that your calculator has. Unfortunately, it does not. So we're going to have to improvise a little bit. I believe on your calculators, if you go inverse norm, it should give you the options for area, mu, sigma, and then like left, right, center, or some junk like that. For the sake of consistency, I'm going to have you keep it on left, because I'd rather not change that. I can't change that on my calculator, although I will suggest something for those who want to see something on their calculator in a minute. But for area, I'm going to put in 0.975. For mu and sigma, I am not going to type in anything, actually. You can leave it as mu is equal to 0 and sigma is equal to 1. Don't change it. If I don't type it in, my calculator automatically assumes an average of 0 and a standard deviation of 1. It automatically assumes that. Now, part of the reason why I'm putting 0.975 in is because if I'm trying to capture the middle 95%, that must mean that I'm leaving out 2.5% over here and 2.5% over here. What I'm hoping to calculate is the z-score for the 97.5th percentile. I need the z-score. This is my critical value. Now, the reason why I said values earlier is because technically the values that I need are positive 1.96, which would be this dot right here, and negative 1.96, which would give me z-scores above and below the average. But more importantly, look at my calculator. Normal CDF, 1.96. Actually, no, I put negative. Negative 1.96, comma 1.96. I'm attempting to capture the middle 95% of data. Now, the reason why I need to show it to you like this is because when you take the AP test, I cannot guarantee that you will be using the calculator that is on your computer. When you take the AP test, you may be stuck with using not this, but a TI-83 piece of garbage. You might be. And if you are, you're going to be stuck with what I have right here. You need to know how to do it this way. If I'm going to capture the middle 95%, that means that I'm not capturing the outer 5%, which is split 2.5, 2.5. Meaning this is the 97.5th percentile. On your fancy schmancy calculators, you can do this. And I would like you to do, I can't type it because I don't have it, but I would like you to do this. You could go back to inverse norm. Second vars, inverse norm. And you could, under the area, type 0.95 and change the word left to center. If you do that, when you calculate it, it will spit out the two z-scores, negative 1.96, positive 1.96, that captures the middle 95%. If you change it to center and have it at 95 or 0.95. Guarantee you it works. But, like I said, I don't have that option on my calculator. And if you don't have that option on your calculator, then your inverse norm is automatically set to the left. So I have to do it this way. I could also do, besides inverse norm 0.975, I could do inverse norm 0.025, and you can see the negative z-score right there. But I digress. Back to dish. Oh, goodness gracious. Okay. So what I'm going to calculate is this. 0.51, which is my sample proportion p hat, plus or minus 1.96 times the square root of 0.51.49 divided by 1,000. Because that's how the formula works. I type in p hat and q hat, and I do that thing there. Yay! All right, let's calculate it and see what we get. I'll have to do it twice. So here, watch me do it twice here. 0.51 plus 1.96 times the square root, 0.51 times 0.49 divided by 1,000, close parentheses. Now, on your calculator, you might, again, have a slightly different interface where You may have to like tab to the right at some point or another because you don't want to add an extra parenthesis in there, but boom, I get that. Now if I want to do the minus, clearly I just got to bring everything back. I don't feel like retyping everything, so I'm going to hit second, enter, and I'm going to change that plus to a minus, and I get that number there. Let me write that down. 0.479, 0.541. There is my constructed confidence interval. That is my constructed confidence interval. Nice. A couple of things before I do the interpretation. First and foremost, if you were going to be 100% confident, what the heck do I type into inverse norm? If I'm going to be 100% confident, it would include this entire thing. What percentile do I put in? Oh, I'm smart, you can clearly put it in. Maybe percentile 1 for 100%. Ooh. You know what that is? That's the calculator saying, please don't do that. Yeah, it's not going to work. What if I would do a -1? Let me see what happens here. Do -1, it doesn't work. Oh, wait, no, of course I can't do -1. Because I'm talking percentiles. Percentiles can't be negative. Maybe if I do 0. See what happens with 0. Yeah, that's not going to work. Back to this. Interpretation. I am 95% confident that the true proportion of voters who will vote Markey is in the interval 0.479 to 0.541. I am 95% confident that the true proportion of voters who will vote Markey is in the interval 0.479 to 0.541. Excellent. Cool. That's the proper interpretation. Now, I do have a little bit more to comment on the 95%. I have a little bit more to comment in terms of changing that. What if I was 99% confident? What if I was 90% confident? What would change if I changed the confidence level? So hold on. 95% confidence produces a Z star of 1.96. If I was now 99% confident, what would happen to that Z star? Well, we'll go back over here. If I'm 95% confident, you don't have to draw this all the time. You can kind of visualize what's going on with this 99% confidence right here. But if I was 99% confident, then I would not be capturing the outer 1%, which means that 0.5% and 0.5% are over here. Which really means that the percentile that I need to calculate for 99% confidence is inverse norm 0.995, because that would be the 99.5th percentile. Okay. Inverse norm 0.995. Oh, what happens here? 2.576. I don't know why I wanted to go a little bit more in terms of the decimals. See, the more confident that you are, the larger that z star is going to be. And if you look back at the interval of p hat plus or minus z star times the standard error of p hat, the more confident you are, the larger the interval. Because that z star is going to affect how big your interval is. If you have a larger z star, then it's going to be adding and subtracting a larger number on your p hat. So if I say I'm 95% confident, then that interval that we calculated earlier is going to be a bit wider. Now, logically, I said before that you can never be 100% confident. I'm going to amend that slightly to say this. I am 100% confident that the true proportion of people who would vote for me for governor is between 0 and 100%. Now think about that statement. That statement's not very helpful. The true proportion is between 0 and 100%. Duh. That's the only way you're going to be 100% confident. The lower the confidence, the smaller the interval. Now, what does that mean? What does that actually mean when I talk about 95% confidence? I want to give a proper interpretation of that. 95% confidence means that if many samples of the same size were taken, confidence intervals constructed, then 95% of those intervals would capture the true proportion. 5% would not. This is a very important statement. When you throw out a confidence interval, it's like throwing out a net into the water to catch fish. Sometimes you capture them, sometimes you don't capture them. The bigger the net, the more of a chance you have at catching a fish. Obviously, if you had a net the size of the lake, then clearly you're going to capture that fish, but sometimes that's not feasible. It's not feasible. Yes, we need a certain level of confidence, but we don't need a confidence interval that's like, the true proportion is between like 30 and 90%. No. We need a decently sized interval. How decent? That's going to be my next statement. But if many samples of the same size were taken and then confidence intervals were constructed, 95% of those intervals would do their job and capture the true proportion, and 5% would not. We, right now, today, you and I, we are just simply hoping that our interval was one of the 95%. This goes back to one of the first statements I made to you earlier today. There it is. I'm just going to bring it back very quickly and then take it away. In confidence intervals, given the sample statistic, we are able to construct an interval that, hopefully, captures the true proportion, or true mean. Hopefully. This whole thing is based on sunshine and hope. I don't know, unicorns. 95% of the intervals would capture the true portion. We're just simply hoping that we're one of the 95%. There's a good chance we're part of the 95%, but that's why we can say we're 95% confident. You could raise that confidence. Now, you could raise that confidence, but there's a direct consequence of this. Margin of error. Margin of error is a phrase that a lot of people are familiar with. The margin of error creates that confidence interval. The margin of error is the plus or minus statement that we talked about. In the interval that we just created, I'll just bring it back very quickly. The interval that we just created, we had a margin of error of roughly 3.1%. Roughly. When you create a confidence interval, your hope is to have a high level of confidence, but a low margin of error. When I say low, I mean like it depends. Do you want like 1% margin of error? Do you want 10% margin of error? Because now watch me, if you increase the size of the interval, by default, you are increasing your margin of error. I'm 99% confident with a larger margin of error. Oh, well, I'm 80% confident with a smaller margin of error, but now you're only 80% confident. That makes a big deal. The gold standard typically is 95%. Some people go higher, some people go lower. But depending on what your confidence is, that changes your margin of error. You could keep your margin of error the same, and you could actually, there's another way to shrink the margin of error. Another way to shrink the margin of error is to increase the sample size. Think about it. This calculation, the standard, move that up a little bit, I apologize. That standard error of p hat is calculated the square root of p hat q hat over n. N is on the bottom of the fraction. N is the sample size. If you increase that value of n, it shrinks the standard error. If it shrinks the standard error, it shrinks the margin of error. Okay, let's do that then. Let's be 95% confident, but let's shrink it as much as we can. How big are you going to go? 10,000 people? 100,000 people? You don't have that kind of money and resources. Think about it. You're actually going out and conducting these surveys. There is a balancing act. Where do we put our confidence? How big of a sample size do we want? Where do we want that margin of error to be? There is a balancing act to this whole thing. Now, there are certain recommendations that people make. Like, I want within this margin of error. I want this level of confidence. Okay, but, we can only have this many people in the survey. Okay, we're going to get into those details. I do apologize. I've taken away all of your snow frolicking time. As a reminder, if you have not left a comment in the chat, please do so. I'm sorry, I got carried away. I typically get carried away with this kind of stuff because it's just incredibly fascinating to me. But leave a comment in the chat if you haven't already. I see all of your comments so far. That'd be great. Thank you. Beyond that, I am going to be assigning that quizzes, as I promised, on sampling distribution. It will be due before class on Monday, and I will be giving you at least 2 attempts at it. So, yay for snow days. It's still coming down. Do you think we'll have school tomorrow? I mean, yeah. My son is adamant that he needs to have school tomorrow because tomorrow is the perfect storm of, in his school, the 100th day of school. Coffee.
Here's the second cup.
I haven't even drunk it yet. It's right here.
I don't know what to tell you.
Well, I appreciate it. Thank you.
You're welcome. Ellie wanted to know if you wanted chocolate chip pancakes.
I would like one.
Okay. Now?
Oh, yes, please. So I can show it off to my students. Okay, hold on. Let me finish my son's statement and then I'll explain what the heck just happened. So tomorrow is my son's 100th day of school, and he is just like, I can't miss it. And tomorrow is also their Valentine's Day party, and he's like, I can't miss it. And I'm like, oh man, I really hope they have school tomorrow. So what just happened is my wife came in the room with a cup of coffee for me. But I already have my cup of coffee right here. I made it before I came in the room today. And she's so very sweet. And then, true to form, as I told you at the beginning of class, she made chocolate chip pancakes. And I'm going to have a chocolate chip pancake. I'm just hoping she brings it in so I can show it off to you so you can all be jealous and think to yourself, oh man, I only have a crummy bowl of cereal. There you are! You want to come here for a second? Here, come here for a second. Let me show you something. Hold on. Hold on a second.
Daddy did this and something this.
Yeah, come here, come here, come here. Come here for a second. Ah. Can you tell everyone what you have? What are you holding?
I'm holding chocolate chips.
You're not just holding chocolate chips, it's a chocolate chip.
I was eating it for a while.
Okay. You tell everyone to enjoy the snow today? Are you going to go out in the snow?
Not right now.
Not right now. Why?
I have to eat this, then I'll go out the snow.
Okay. Then you have fun then. Thank you for the pancake.
You're welcome.
Okay. Oh, goodness. Anyway, I made you sit through that. Oh, my. Anyway, that's it for me. I'm going to sign off. I apologize for making you sit through my chocolate chip pancake. Look at that. Look at that. Look at that chocolate chip pancake. You need to be jealous of that chocolate chip pancake. Because I'm going to eat that chocolate chip pancake. Alright. Class dismissed. Oh, goodness gracious. Alright, go home. Go. Do your thing. This is where the end credits. I really should have like an end credits to my videos or something like that. Okay, no one's actually leaving. This is making me feel weird. Everyone get out of my house. Fine, I'll sign off.